In the last few lectures, we were discussing the process synchronization. At the end of the previous lecture, we presented the problem of dining philosophers and showed that there may be a problem of deadlock. To start the discussion of the deadlock, let me reproduce the problem of dining philosophers once more. Here is a round table. There are 5 philosophers, P0 to P4. 5 plates are there. There are 5 forks, F0 to F4. Each philosopher thinks, and when he feels hungry, he picks up the left fork first, then he picks up the right fork, and then with the help of 2 forks, he starts eating. Now, both the 2 forks are necessary for eating, and therefore, they have to, each one of them has to pick up both the forks. Now, that's as such is a normal situation. It may continue as long as the situation does not turn out to be like this, that simultaneously each of the philosopher picks up the left fork, then wants to go for the right fork. Now, there will be no right fork because it has been picked up already. Then in that situation, all the philosophers will wait indefinitely. Okay. Now, you see that this is a situation of deadlock. Essentially, very respectable philosopher in a very undistinguished manner is waiting in a hungry state, but cannot do anything, and possibly they will starve to death. Okay. This is the problem of deadlock. In our operating system's parlance, these philosophers are the processes, and the forks are the resources. Okay. Let us try to analyze the problem and see what are the things associated with deadlocks. Now, the situation here is this, as if, say, there are 5 philosophers and the philosophers I have drawn in green. Say this is philosopher 0 or process 0, this is process 1, this is process 2, 3 and process 4. Okay. There are 5 forks, say this is a fork, this is a fork, this is fork 0 or resource 0, fork 1, fork 2, fork 3 and fork 4. Okay. They are our resources. Okay. Now, each philosopher has got 1 fork. That means 1 fork is attached, 1 resource is attached to this process, F0 to P0. Similarly, this is the situation. And in this situation, each philosopher is now asking for another fork. Okay. And immediately you see all the processes P0 to P4 will be waiting, okay, for the other process to release a fork, to release a resource, and they will be waiting in a circular manner. Okay. Now, this is the situation which may give rise to what I say that deadlock, right. Now, let us see. This is the situation of our, of the philosopher's problem. Let us now try to generalize and see what are the different aspects that are associated with the deadlock. Okay, but let us first see our system model. Our system model is this. There are some resource types, as I say, R0, R1 to say Rk minus 1, the K resource types. These resource types may be I/O devices, right? So, for example, Mac tapes, printers, scanner. memory blocks, CPU cycle, files, all of them will take as resource types, right? Now, each resource type Ri may have TI instances. For example, there may be 10 MACTEVs, 5 printers, 2 scanners, several mega memory blocks, and so on. Okay, several thousands of files, etc. Okay, for each resource type Ri has TI instances, right? And each process executes the following sequence to utilize the resource. For example, if a process needs a resource, then it should request for the resource. If granted, it will use the resource, and after the use, it must release the resource. Therefore, this is the sequence in which the process should utilize a resource. First request it, then use it, and then release it. Okay, this is our system model. And now let us see what are the necessary conditions of a deadlock. Okay, the necessary conditions of a deadlock is mutual exclusion. That means there should be at least one resource which is unshareable, and therefore has mutual exclusion has to be enforced to utilize it. Let me repeat once more. There must be at least one resource which is unshareable, and mutual exclusion has to be enforced so that that resource can be utilized. Similarly, second situation is hold and wait. Hold and wait is that there must be at least one process such that it is holding one resource and then it's waiting for the other resources to be released which are being held by other processes. Okay? Let me repeat that there must be at least one process which is holding one or more resources, okay, at least one resource, and it is waiting for other resources to be released by other processes. Okay. Third is that no preemption allowed. That means that the resources that are being held by processes cannot be preempted. They can be only released by the processes on termination. Okay, on their own sweet will, they will release it. And circular wait, the circular wait is essentially that what I have already depicted, that this is a circular wait. Say P0 is waiting for F1 and so on. This is a circular wait that has to exist. Now let me emphasize one thing, that all four necessary conditions has to hold simultaneously for a deadlock. For a deadlock may be possible. Okay, for that a deadlock may be possible. Now, to analyze this problem, I should say methodically, let us now introduce what we call that resource allocation graph. Right? Now, in the resource allocation graph, we'll have a set of vertices we call V that we partitioned into set of processes and set of resources types. Okay, the set of processes, say P is P1, P2 to Pn. Okay, say n processes are there. The set of resources types are, which is R1, R2 to Rm. Therefore, n processes are there and m resource types are there. Okay, the whole that set P and set R together constitute the set of vertices. Okay. Now E is a set of edges. Now the set of edges is a directed edges. Okay. That directed edges can be of two types. One we call that assignment edge, say Ri to Pj. Here you see that there is a resource, okay, type in which there is one resource. That Ri to Pj is an assignment edge, which means that Ri has been allocated to Pj, which means Pj is holding Ri. Okay, and there is a request edge, say Pj to Ri. That means Pj is requesting for one instance of Ri. Okay, that is depicted by means of this black arrow. They are directed edges. Okay. To clarify further, these would be the symbols that we will use in our subsequent discussion. Process will be shown by a circle, okay, the green circle. Resource type will be shown by a red square. Okay, for example, this is a resource type with 5 instances, say 5 actives, right? Now, PJ requesting an instance of Ri will be shown this way, that PJ is requesting an instance of Ri, and PJ holding an instance of Ri will be shown this way, that one of the instance is being held by PJ, right? Now, let us see with these symbolisms and definitions, let us give an example of a graph, right? That resource allocation graph. Here you see that I have drawn four processes, P1, P2, P3, and P4. 4 processes are there. 4 resource types are also there, say R1, R2, R3, and R4. Okay. Now, you see that one instance of R1 is held by P1, second instance of R1 is being held by P2, right? Similarly, there is only one instance of R3 which is held by P2. There are 2 instances of R2, one is held by P2, another is held by P3. Okay. When I say that instances of resource type, intrinsically we mean that if a process wants an instance of the type, okay, any one given to it should serve the purpose, okay, which means that, for example, say there are 5 MACtives, right? Say process wants a MACtive. One MACtive, any one of these 5 MACtives given to the process should satisfy the need of the process, okay. Now, here is another process of P4. R4 is a resource type with 3 instances. 1 have been held by P4. Now, since there is no cycle, but when we see the cycles, we take the directed edges, both the assignment as well as the request edges. Okay, since there is no cycle, right, there is no possibility of a deadlock, right. For example, it is a situation here that P1 is waiting for R2, no doubt. P3 is waiting for R3, no doubt. But P2 has all the resources, and therefore P2 will logically conclude sometime. When P2 concludes, it will release R1, one instance of R1, R3, and one instance of R2. Now, since the moment that R3 is released, that R3 can now be allocated to P3. Therefore, this request stage will be converted into now assignment age. Similarly, that this request stage will be converted to an assignment age. Since this instance will be released by P2, then both P1 and P3 now can complete, and therefore there is no possibility of a situation of a deadlock. And P4, you see, is not waiting for anybody, any resource to be released, and therefore P4 can logically come to its own conclusions. That means it can finish without any problem. But this is quite fine. But suppose that P2 at this instance of time, okay, now puts a request for R1, right. Now you can immediately see that there is a cycle, okay. The cycles are say that P1, then P1 to R2, then R2 to P2, then P2 to R1, and then R1 to P1. Therefore, this is a cycle, and here another is P1 to R2, then R2 P3, P3 to R3, R3 to P2, P2 to R1, and then R1 to P1. You know, there are 2 cycles, minimal cycles that exist. Okay. Now, under this situation, you can see that there is deadlock. Okay, because now P2 will be waiting for this release for getting an R1. It will not get, therefore P2 cannot release any of the resources, therefore P1 and P3 will release, okay. And in such a situation, there will this particular instance will go to a deadlock, right. But the situation is, I'll show just by an example, that if a particular resource type has more than one instances, just the existence of a cycle may not lead to a deadlock. Okay, we'll come to this situation. But as I showed earlier by the earlier diagram, that if there is a single instance of the resource types, say here the single instance of R1, single instance of R2, single instance of R3, and there is a cycle, okay, in that case, the system at this state will go to a deadlock situation, okay, that it will lead to a deadlock situation. Now, that the circular weight may not lead to a deadlock when there are more than one instances of a resource, okay, has been shown by means of this diagram. Say this is a resource type R1, say this is a resource type R2, okay. Here you see that P1 is holding an instance of R1, P2 is holding an instance of R2, okay. Now P1 has requested an instance of R2 and P2 has requested an instance of R1, right. Now you see one instance of R1 has been held by P3 and one instance of R2 is being held by P4, okay. Now naturally you see that here that P3 and P4 is not waiting for any other resource and therefore P3 can conclude, it can finish and therefore release that instance of R1. Similarly, P4 will finish and release the instance of R2. Now in that case that R1 can be allocated to P2, okay, therefore this request stage will be converted to an assignment stage. Similarly, this request stage will be converted into an assignment stage and there will be no circle, I mean the cycle over here, and both P1 and P2 therefore can conclude, okay, which means that once more let me repeat that even if there is a circular weight, but if there are more than one instances of resource types, then deadlock may not happen, okay. Now these are the things that we'll have to remember when we deal with deadlocks, right. Therefore let's see what are our basic points, right. The basic points are that there should not be, I mean if there is no cycle and that means that implies that there is no deadlock, okay. No cycle, no deadlock. Now if a cycle exists and if only one instance per resource type is there, then it implies that there is a deadlock. That is, but if several instances of a particular resource type exist, then there is a possibility of a deadlock, but it may not lead to deadlock, okay. It means that is basically there is a possibility of a deadlock. It may lead to a deadlock, it may not lead to a deadlock, as has been shown by the previous examples, okay. Now that's the situation of a deadlock. Now you can see immediately that deadlock as such is quite a problematic situation when many processes are executing inside the system. We should do something about it. Let us see what we can do about this. How do we handle the deadlock? Okay. Now we should ensure that deadlock never occurs. One way of handling is that we ensure that deadlock never occurs. That means we try to prevent and we want to avoid, okay. Prevention and avoidance. Prevention is that you allocate resources from the very beginning in such a way that there is no possibility of a deadlock, okay. That is the prevention. And avoidance is that you go on allocating the resources, okay. And every time you allocate a resource to a process, you check that whether the situation is safe or not. That means whether after allocating this resource, there is a possibility of a deadlock or not, okay. There may be a deadlock, there may not be a deadlock. But if there is a possibility of deadlock, then don't allocate the resource to this process, let this process wait. Okay, that's the avoidance. And the second option is that let us be a bit daring. Okay, here we are a bit conservative. Let us be a bit daring and allow deadlock and then detect it and try to recover from it. Okay, that means allow deadlock, let the processes go, whatever resources they want, you go on allocating it, then check whether there is a deadlock or not. If there is a deadlock, you try to recover from this situation, right? And there is a third possibility. We'll see what is this third possibility later on. Now, to prevent deadlock, as I say, the prevention means that you allocate the resources at the very beginning in such a way that there is no possibility of a deadlock. Okay, that is our prevention. Now, to do that, we should ensure that at least one necessary conditions is not satisfied. We say that there are 4 necessary conditions. Let us see what are the 4 necessary conditions once more, because that's important. Sorry, these are the 4 necessary conditions. One is that mutual exclusion, hold and wait, no preemption allowed, and circular wait. Okay, these are the necessary conditions, all of which must simultaneously hold. Right. Now, to prevent deadlock, we do that at least one necessary conditions is not satisfied. Let us go one by one. First is the mutual exclusion. That mutual exclusion, it is necessary if there is some unshareable resource. Okay, right. So, for example, a Mac tape. A Mac tape is an unshareable resource, or a printer is an unshareable resource, which means that if some process is using Mac tape, other process cannot be allowed to use that Mac tape, and therefore they have to use the Mac tape in a mutually exclusive way. Right. Now, in that case, the denying mutual exclusion, that means not satisfying mutual exclusion, is difficult to achieve, right? Therefore, mutual exclusion, if it is there in terms of some non-shareable resource, okay, you will have to obey it, and therefore denying that condition, necessary condition, may not be achievable. Okay. Now, let us come to the second, that hold and wait. Okay. In the case of the hold and wait, what we can do is that 2 ways we can treat. Okay, that we say that request all the resources in advance in the beginning and allocate these. And if it is cannot be allocated, okay, then don't allocate any resource at all. Let the process wait. Okay, let me give an example. Say a process, right? Say a process, say from Mac tape is copying into a disk file, and then, so for example, it is sorting here. The disk file is being sorted, and then it is sent to the printer. Okay, the Mac tape, some data is here. It is being taken into a disk file. Here it is sorted, right? And after sorting, it's kept in another disk file, and then from that disk file, it is printed. Okay, through the printing process, right? Right, maybe same disk file or another disk file. Okay. Now the thing is that when a process needs now the Mac tape, a disk file, and a printer. In these situations, hold and wait, the process has to request the Mac tape, the disk file, and the printer at the very beginning. Now, if any one of them is non-available, in that case, the process must wait. Okay. To will be waiting till all the resources are available, then all the resources will be allocated to it, and only then the process will continue. Okay. This is one way of handling this. Another is that instead of allocating all the processes, then the process request in advance in subsets as needed, then release all of them, and then request for another subset. Okay. Let me exemplify it once more by this example. So, for example, initially the process will need the MACTAB and the disk file, and therefore what it does is that it requests for this one, okay, the MACTAB and the disk file. This allocated, the process then copies MACTAB to disk file, and then the disk file is shorted, then disk file is only needed, and next the disk file to printer. Okay, these two resources are allocated. Therefore, the process first request for MACTAB and the disk file is granted, it continues. After that copying is over, then it is sorting it, and after the sorting it, now after that copying is over, the process releases both the MACTAB and the disk file. Now, after the copying is over and sorting, it will need the disk file and the printing once more. Then it will request for the disk file as well as the printer. It will be allocated, and after the operation is over, it will release both the disk file and the printer. That is why here we have said that the process has to request in advance in subsets as needed, but release all of them before requesting another subset. Okay, this is important. Now, naturally, you see this hold and wait is essentially a conservative technique of preventing deadlock that may lead to, and that I should not say may, it mostly will lead to low resource utilization, because you know that this, say for example, the MACTAB or the printer may not be needed for the entire period, and therefore the MACTAB and the printer will be held by the process till it is released, and therefore the resource utilizations will be low, and it may lead to possible starvation, because you see that if there are popular resources and many processes want them, and the process cannot move without these resources, okay, it has to wait. In that case, naturally, a process may starve, right? Therefore, the disadvantage is that that's low resource utilization and possible starvation, right? Now, let us come to the third condition, that is no preemption allowed. Okay. Now, only negation of no preemption is preemption, and as I said, that preemption is difficult because the preempt resources from the current, I mean, that can be two ways. If preemptions can at all be allowed, okay, that preempt resources from the currently requesting process, that means the process which is requesting another resource and has to wait, right? Then all the resources held by this process are preempted, sent back to the reserves, okay, and this process will be allowed to continue only after that all the old resources that it had requested and the new resource for which it has requested can all be allocated, right? This is one way that you can do it. Another is that when that a resource is requested by a process, then preempt the resources from other processes and give it to this process so that this process can continue, right? Now, this preemption may not be possible, as I said, that in the case of a non-shareable resources like say printers and tape drives, and therefore it may not be achievable at all. Okay, let us now discuss the fourth preventive technique, that is ensuring that the circular wait does not take place. Okay, let's come to it. That to ensure that no circular wait happens, we will do this, that we will impose a total ordering on all resources types, and then enforce that each process requests resources in an increasing order of enumeration. Okay, two things are involved. One thing is that impose a total ordering on all resource types, and the second is enforce that each process requests resources in an increasing order of enumeration. Let us see that what does it mean. Let us elaborate it. Okay. Say this is a set of resource type R. Rm number of resource types are there. Now we define a one-to-one function that f on R maps onto n, which is a set of natural numbers, right? It can be like this, that say f of magtape, we say this is 2, say f of disk drive is equal to 7, say f of printer is equal to 11. Now, say a process requested magtape and got it. Now the process wants to get either disk drive or printer. Now, if it requests disk drive, then since f of disk drive is 7, which is greater than f of magtape, this request can be made. Or similarly, the request for printer can be made. But if the process is holding the printer and wants to request either disk drive or magtape, since f of disk drive or of f of magtape is less than f of printer, right? Therefore, disk drive or magtape request cannot be made by the process once the process is holding printer. Okay, this is that what we meant by that we define a one-to-one function and we say that a process can request Rj after Ri if and only if Frj is greater than Fri. Otherwise, this process, that request cannot be made. Right. Another important thing is that all resources of same type must be requested simultaneously. That means if one wants to use magtapes, all requests for magtapes have to be made simultaneously. Now let us see, by fulfilling this, how do we prevent the deadlock? Okay. So let us take an example. Say we have several processes. So this is P1, the process P2, P3, and so on. So we have the process Pk, and we have resources, say R1, R2, R3, and the situation is that R1 is being held by P1, R2 is being held by P2, R3 by P3, and Rk by Pk. And P1 now request R2. So for this age will be there. This request can only be made, as I say, that if Fr2 is greater than Fr1, or in other words, that if R1 is less than Fr2. Similarly, if now P2 wants to request R3, then Fr2 must be less than Fr3, and so on. This must be less than Frk, and if now Pk wants to request R1, then Frk must be less than Fr1, which is a contradiction. Okay, and in that case, since Fr1, by this transitivity, that Fr1 is less than Frk, and here if it wants to request, then Frk has to be less than Fr1, this request cannot be made. Okay, by this contradiction, it's proved that if we ensure the protocol that whenever one process wants to wants another resource and wants to request it, that f of that resource, that fr3 has to be greater than fr2. Okay, if we follow this protocol, in that case there can never be a deadlock. Now this is the fourth deadlock prevention technique that we have described. Therefore, we have described in fact preventive techniques that depends upon denying one of the necessary conditions that have been listed here, say mutual exclusion, hold and wait, no preemption allowed, and circular wait. And as I said earlier, which I am repeating, this being a very conservative technique, preventing deadlock, the resource utilizations will be poor. That means possibly a process will acquire a resource which it does not need immediately, okay, and therefore the resource is not being utilized to the full extent. Now that's all so far as the preventive technique that we wanted to say. In the next lectures, we'll be discussing about that avoidance techniques and the detection techniques. That's all for today's lecture.